Hello and welcome to another video. Today we're going to be working on combinations. So in this problem you're given an integer n and k and you want to return all possible combinations of k numbers chosen from range 1 to n. And you want to return the answer in any order. So you have n equals 4 and k equals 2 here. So in this case, if n equals 4 and k equals 2, that means that we're trying to get every single combination here. And so the trick with combinations, to make it really easy to get all the combinations, is as opposed to permutations. Right? So permutations, you want 1, 2, and 2, 1. But in this case, you don't, right? So you don't want 1, 2, and 2, 1. You just want 2. We just want 1, 2. So if you think about it, if you look at all these, you can see that the number to the left is smaller than the number to the right. So all you would have to do for these is, for your number to the left, you would loop through this list. And then the next numbers would have to be greater than that number, right? So the way it will look is like we'd have 1, 2, 1, 3, 1, 4. So if you just keep this ascending order, then you're ensuring that you're never having any duplicates. And it's pretty straightforward to do that. And that's how you would do combinations. And so for 2, then you would have 2, 3, right? 2, 4, 3, 4. Okay. So we have 20 here, and the time and space complexity for combinations is just kind of annoying, but basically I'm going to show you like the standard way to get combinations. It's going to involve backtracking, and yeah, so what do we actually need to do in this problem, right? Like how do we approach it essentially? So what we actually need to do is we need to loop through the numbers, and then we need to add a number, and then we need to keep doing that. And so I'm going to show you the boilerplate template for that. So let's take a look at that, right? We're going to have some array, like let's say for this case, right, we're trying to get 4 numbers. So essentially what we're going to do is we're going to loop through numbers, and we're going to be pushing and popping numbers. And so what that's going to look like is we're going to have a local array that we're going to add numbers to, and then we're going to have a global array that we will be pushing results into, right? So we'll have like a result, and we'll have this. And so what happens is like it'll loop, and then it will try to get all the numbers in here, and then it'll loop again. So for example, it'll loop through the first 1 through 4, it'll add a 1, and then it will go into the next state, and then we'll loop. But now we're not looping 1 through 4, we're actually looping 2 through 4, because we're going to be looping, if this is I, we're going to be looping at I plus 1 at every next index. So if we have some more stuff, it'll be like I plus 1, I plus 2, and so on. Okay. And so here we're going to get 1, right? So if our numbers are 1, 2, 3, 4, let's just say we have like an array of 1, 2, 3, 4, we're going to get 1 here, and then we're going to get 2 here. And then what's going to happen is we're going to say, okay, we have the length we want. We have 2 length. So then we're going to put this 1, 2 in here, right? And then let's actually add another color. So then what's going to happen is we're going to go back, and we're going to say, okay, we put in the 2, but let's try other numbers, right? Let's try more numbers. So we also have a 3 we can put in. So we're going to put in a 3, and then we're going to recurse again. So we're going to put in 1, 3 here. So we're going to put in 1, 3. Now we're going to go back, and then we're going to say, okay, let's take out the 3, and let's put in a 4. And now we're going to put in 1, 4. And then we're going to take out the 4, and we're going to go back to this 1 now, right? We went through every single number with 1. Now we're going to say, okay, let's change this 1 to a 2, right? We're going to be looping in every single case. We're going to be looping. So here we're looping from I plus 1 from I to the end. Here we're looping from I plus 1 to the end. So this will loop 1 through 4. And then this will loop 2 through 4, right? It won't necessarily loop 2 through 4. It'll be whatever this I value is. It'll loop I plus 1 to 4. So really, let's write that. So it's going to be I plus 1 to 4. Okay, so we're going to put in a 2. Then we're going to go back here, and we're going to say, okay, what are we looping from with a 2? So it has to be every number that's bigger than 2, right? So we're going to have a 3. And now we have 2, 3. So we're going to write that in. And now we're going to get rid of this 3, right? And we're going to say, is there any other number? Yes, there is. There's a 4. So we're going to put in 2, 4. And we're going to run out of space here, but I'll just add some more. So now we're down with the 4, which means we're going to get out of this loop. We're going to go back here to this 2, and we're going to say, okay, let's go to the next number, right? We're looping 1 through 4 here. So it's going to be a 3. And now for the 3, we're going to put in a 4. That's the only number that we can have. So we're going to add 3, 4 into this result. Then this 4 gets out of there. And now we go back to the 3, and we say, what's the next number? 4. And so we're going to add a little optimization. And this optimization is going to say, okay, how many numbers do we need? And do we actually even have enough to do this, right? Like for this 4, we're going to say, okay, we need 2 numbers. We're at this index. Are there even 2 numbers left? If there's not, we're just going to return straight away because there aren't 2 numbers here. So we don't need to put in this 4, right? We can just return straight away. And this is going to save us a lot. For example, let's say k is like 18 and you have 20 numbers, right? So you have 20 numbers 1 through 20. And all of a sudden you're at like number, let's call it 4. So you have 4 through 20. And how many numbers is that total? So you have 20 minus 3. So you only have 17 numbers. So if you have 17 numbers here, like if anything that starts with 4 isn't going to work because you don't have enough numbers. Anything that starts with 5 is not going to work. Anything that starts with 6. And so this is going to save us a ton for the bigger problems, right? Like we can just right away say how many numbers do we need? How many numbers do we actually have? And if we don't have enough, we're just going to be done with that right away. Like we're going to say, okay, from 4 onwards, we don't need any of that looping. We're done. We're only going to be looping from 1 through 3 because those are the only numbers. So we're only going to take numbers that start with 1, numbers that start with 2, numbers that start with 3. And in the subproblems, it's going to be the same thing, right? Like you're not going to have a number that starts with 2 and then the second number is like a 10. Because when we get into this 10, we're going to say we need 17 numbers now, and there's just not enough numbers here. So in the subproblems, we're going to also be checking for this recursive case where we're going to be taking out things that are invalid. And so the main thing to take out of this is combinations versus permutations. So for permutations where duplicates are allowed, right? If you can have 1, 2, and 2, 1. The difference here is instead of looping where you're doing like I plus 1, I plus 2, and so on, you would actually have the same index multiple times. So you would have, I to n, and then the next loop would loop I to n, and so on. And that would allow you to have 1, 2, and 2, 1. But if you don't want duplicates, and there's a lot of problems where you don't want duplicates, what you're going to want to do is you're going to always want to be looping, I to n, and then the next loop needs to be looping I plus 1 to n. And this is really common in a lot of DP problems as well, where you don't want duplicates, all right? In some coin change problems, you don't want duplicates, like you don't want to use coins 1, 2, and 2, 1, and things like that. So in that case, you're actually going to want to make sure you do this. So that's the key, is combinations do this, permutations do this. Just have a bunch of these, and combinations do this one. Okay, so now we know we're going to be coding, and I'm going to kind of show you the boilerplate template for backtracking combinations. Okay, so let's do that. So what you're going to want to do for backtracking and combinations that works really nicely is you have a result, and you also have a current, and this is going to be the current combination. So we can maybe call it like comb or something. And essentially we're going to have a function, right? So we're going to call that maybe backtrack or something, right? It's going to have an index. Let's call that I. And what are our actual base cases, right? So we have a couple base cases. If the length of the combination equals k, that means our combination is big enough. Like we filled up this array with enough characters to actually append it to the result. So if that's the case, we're actually going to append a copy of k. The reason you want to append a copy is because we're going to be modifying this combination. So if you just append this, we're going to be modifying it later, and that's going to screw up the result. So every time you append, you want to append a copy, and that's going to be useful. Let's actually fix our tabs here. So that's one base case, and then we can just return right after we append. Okay, now another case, and this is going to be our essentially, or sorry, this is another case, I guess, but I don't think you'll actually ever get there. Yeah, I don't think we need it, so I think we could skip that one. I was going to say, like, if the index is greater than n, we can return, but I think we're going to be checking for that in our actual recursive case. And so to actually calculate like how much space you need and how much space you have, it's actually n minus I, and I'll explain it in a second, plus 1 is less than k minus length curve. So it's actually k minus length curve. Let's just explain that for a second. So let's say we have an array like this, right? And we need 3 elements. So let's say we are here. This is going to be index, and we have let's say we have an empty array, right? We have an empty array so far. We need 3 elements. Let's say we are, this is our empty array, and this is the full array. And so we are at like this index, and we have currently the array that we have is no elements. So how many elements do we have total? We should have 4, right? So let's just double check if that works with our equation. So n is 5, right? N minus I So we're actually going to initialize I to 1 here. It's not going to be the index. So it's actually going to be 5. Like we can write that out, right? So 5 minus 1 minus 1 is going to be less than 3 minus 0. And so this is actually 3, and 3 is not less than 3. So this is going to be false, which means we're going to have a valid thing here, right? I think I said here, right? Or maybe I said on this third one. Oh, let me just double check this one more time, right? So let's say we're on this third index. If we're on this third index, let's say we are on 3. So it's going to be 5 minus the index we are on, which is 3, plus 1. It's actually plus 1. I think I did minus 1 is less than 3. So here, it's actually going to be 6 minus 3. So yeah. So on this third index, this would not be true. And so we do have enough elements, which we should, right? If we're on this third index, we can just take 3, 4, 5. But let's say we're on the fourth index, and we still have nothing, right? So then what would happen? We would be, n would be 5. The index would be 4 plus 1 is less than, we want a, how many? We want a 3-element array? Yeah, and then length cur is 0. So now what do we have? So now we actually have 5 minus 4 plus 1 is going to be 2, which is less than 3. So right now we just say, like, let's just return right away. And this is going to save us a ton of space for the bigger problems, like I said, because imagine k here is 18, and you have a bunch of numbers, right? Then you can say right away, like, oh, anything that starts with 3, no good, let's just get rid of all of that. So that saves us, you know, a ton of space, because the complexity for this is really bad. So any optimization is going to be quite helpful for you. Okay, so this is going to be the case where we just don't have enough elements to write in. So we're going to just, obviously, what are we going to do here? We're just going to return. And now we're actually going to do our backtracking case. So we're going to say for j in range j, or sorry, it's going to be I, and then it's going to be n plus 1. So essentially what you want to do, right? So if you think about it, like what would the range be? So let's say this I, let's say we have an array 1 through 5, right? And we are at the first thing. So we're going to pass in 1 here, right? So if we're passing in 1, the first number we want to try is 1, and the last number we want to try is 5. So that's why it's 1 to n plus 1, so that will be 1 to 5 if we're on 1. Okay, so what do we actually want to be doing here? So we want to append the number to the current array. Now we want to call backtrack, and we actually want to put in the next number, right? So let's say we append 1. If we append 1, what do we want to do? We actually want to, for the next part, go to 2, right? So the next part should start at 2. We shouldn't be starting at 1. We shouldn't, otherwise we can have duplicates, right? So if we append 1, we want to start the next one at 2. So that's why it's j plus 1, like I talked about before, because we're doing combinations, not permutations. Now you append, you backtrack. Now that we're done, we're going to pop, right? And this is how the backtrack works. You fill out the cur. So for example, let's say we have like 1, 2, 3. Or let's say we have 1, 2. We're going to be like, okay, we have something valid. We're going to push. Then we're going to return out. And then this is when we do this pop. And then we're going to pop the 2. And now we're going to try like a 3. You know, do something, pop the 3, try the 4, and so on. And then finally, when you pop everything and you're done, then you'll go back into your first backtrack and you'll have nothing in here. Then you'll try like a 2 and then so on. So that's why, so this is the template for a backtrack. You want to do something, you want to call backtrack, and then you want to modify what you did. And so we're going to have cur.pop. And now finally we have to actually call this backtrack function. And what are we, what element are we starting at? So we're starting at 1, right? We're doing 1 through n. Okay, now finally we can return the result. So let's take a look at that. Okay, length cur, this is comb, right? So comb, because we call it for combinations. Usually I use cur for most of my backtracking stuff, so I had it like that, that's okay. Okay. And let's actually look what will happen if we don't do this copy, just out of curiosity, right? So you see this is correct, but let's see what happens when we don't do a copy. So you could see these are all empty, right? Because we are saying, okay, let's append comb, but then we're actually deleting from it. So then that's why you want to do the copy. Because if you don't do the copy, then you'll have this kind of thing. You always want to make a copy when you are going to be changing your array in the future. Okay, so now we want to submit. And so you can see it's quite efficient. And for the time and space complexity, it's going to be a pain, but let's kind of go over it. So the number of combinations for like the normal of combinations is actually n choose k. And the way that the number that is, I believe, I think it's like n factorial over, someone can correct me if I'm wrong, like I haven't done this in a while. I just like looked up the formula for this. So it's n minus k factorial. So this is like your formula. It's this over this. And this is how many combinations you have, right? But we also have to build the combinations. And how long does it take to build one combination? Well, worst case scenario, it's actually not going to be as bad, right? Because you're not building them from scratch. But theoretically, worst case scenario, if you did build them from scratch, would be k length, right? Like if a combination is 18 letters, or yeah, 18 numbers, it's going to take 18 to build that combination. So it's actually going to be this whole thing is like the worst case, but the reason it's going to be really tricky to find the true complexity is because it's really hard to say like how much this saves us. It's also really hard to say like we're not truly building these from scratch, right? Because think about it, like let's say we have 1, 2, 3, and we push that, then we delete a 3 and we add a 4. So we made a combination, but we actually made it in, we didn't have to write the whole thing. And in an extreme case, let's say we had like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that's one combination. We append that, then we delete 10, we add the 11. Like this didn't take us 10 times. So you could argue like maybe this is O of 1 and it's like something like this. And then also, how much does this part save you where you're essentially, saving some time there and so on and so on. But this is the number of combinations, and I think that's like, it's kind of hard to explain the exact time complexity. And you might think like, the truly worst case time complexity is going to be actually something like n to the k if you think about it, because it's going to be n factorial, because if you think about it, this loop, like how long would that run, right? So let's just think about it. So let's say it's like I through 20, or like it's actually going to be so worst case scenario, let's say k is like 20 and or k is not 20 but k is like 18. So you would have 18 numbers, so it would be like 18 times 17 times 16 times 15 times something along those lines. And so it's going to be not that good, but yeah, either way. So the number of total combinations you have is this. So I would say that I would argue that this is like the total time, and then whatever time you think to build each combination, whether you think it's k or 1 or whatever, you can write that. Okay. And yeah, so I think there's like n choose k, and then there's also like permutations, which is like it's NPR or something, but that's the case for this one. Not going to go more in detail on that. I think I spent enough time as it is. Okay, and so now for the space, if you think about it, so if we're not counting the result, if we are counting the result, it's pretty straightforward, right? Like we would have n choose k combinations, and then each combination would be k length. But assuming we're not counting the result in our space, which usually you don't, then we're just using this combination. So this combination is only length k. So we're essentially reusing our space over and over and over, and then we're just storing stuff in the result. Okay. So hopefully you learned the difference between combinations and permutations, and I know that you're going to want to know how to do these unique combinations for harder problems, because they will come up in DP and other stuff. So definitely figure out, make sure you really understand, like, I would understand the backtracking, and I would also understand how do you get unique combinations in the future. Make sure that you're actually doing this like j+1 all the time instead of reusing numbers. Okay, but that's going to be it for this problem, so hopefully you liked it, and if you did, please like the video and subscribe to the channel, and I will see you in the next one. Thanks for watching.